This is part B for our unit on confirmatory factor analysis, and the next issue to talk about is the issue of identification. So in our previous video, we went through all the steps of building a confirmatory factor analysis model. We looked at different ways of specifying or describing a confirmatory factor analysis model. And we are just about ready to go on to talk about how we would actually run a confirmatory factor analysis, how we would get estimates for the parameters that we want to estimate. We would get parameter estimates, and how we would test the fit of our model. But before we go on to actually test a confirmatory factor analysis model, before we do that, we need to make sure that the model is identified. So I suppose that raises two questions. The first question is, what do I mean by identification? What does it mean to say a model is identified? And then the second question is, well, how do we go about making sure a model is identified? So for the first question, what does it mean to say a model is identified? To say a model is identified says that when we do our confirmatory factor analysis and we get parameter estimates, that there is just one single solution that produces the best fit for our model. So if one single set of parameter estimates, certain values for our parameters, if we can identify values for our parameter estimates, and those values produce one single solution that has the best fit for our model, then the model's identified. A model would not be identified if there were many different possible values that our parameters could take on, and all those different values produced equally good fit. And it wouldn't, in this case, it wouldn't be possible to identify one best model because there's many different possible solutions and they all work equally well. To illustrate the basic idea here, I have, say for identified, I have a basic algebra equation. So if I say the number 54 is equal to 2x times 4. And that's an equation that you could solve. If we plugged in the number of, say, 25, 2 times 25 plus 4 equals 54. So we could solve this equation. There's just one answer that would solve this equation. X equals 25 would solve that equation, so it's identified. This equation down below, if I say 54 is equal to 2x plus y, well, now there's many different possible solutions that could solve this that would make it correct. And so I'd say this equation at the bottom, because there's many possible solutions, is not identified. So that's another illustration of what I mean by identified. Identified is when there's one single solution to my problem, or to the formula or the model I'm trying to test. And not identified is when there's many possible solutions and they all produce equally good fit. So how do we go about making sure our models are identified? There's three key issues that we need to address, and if we address these three issues, or three potential problems that might make our models not identified, if we address these three issues, then we can be assured we will have an identified model. Now the first issue, or the first potential problem we need to address to make sure that we have an identified model, is one we've already talked about. It has to do with degrees of freedom. Simply, we cannot have a negative degrees of freedom. I've talked about that before, and in our previous unit on structural equation modeling, we talked about that. And the reason why our degrees of freedom can't be negative is because if we had negative degrees of freedom, the model would not be identified. Now, if we have 0 degrees of freedom, that's when the number of elements in our variance-covariance matrix are exactly equal to the number of parameters that we're estimating in our model. We talked about how that would be a saturated model, or another term for that same thing is a just identified model with 0 degrees of freedom, saturated, or we could also call that just identified as another term that people sometimes use to describe a saturated model. And previously we talked about the fact that we can get parameter estimates for this type of saturated model, but it wouldn't be something we would use to test fit, because if our model is saturated, it will always produce a perfect fit. The reconstructed variance-covariance matrix will always be identical to the actual sample variance-covariance matrix when we have a saturated model. So it's one we could use a saturated model to get parameter estimates, but we would not use this to test fit, because if the model is saturated, the fit would always be perfect. And this is something that it's mathematically feasible to do, but in terms of confirmatory factor analysis, we wouldn't ever do this because one of the key things we want to address in confirmatory factor analysis pertains to the fit of our model. So if you're doing confirmatory factor analysis, you would never be using a model with 0 degrees of freedom. You wouldn't use a saturated model to do confirmatory factor analysis. So when we're doing confirmatory factor analysis, we're always going to have a positive non-zero degrees of freedom. That is, we're going to have constraints on our model that make our degrees of freedom larger than 0. And that means that our fit will not be perfect, and we can test the fit of the model. We can test and see how well our model fits. That is, the assumptions based on the constraints that we placed on our model. How reasonable are those constraints? And this, like I said down at the bottom here, this will always be true when we're doing a confirmatory factor analysis. We should always have degrees of freedom greater than 0. So in general, if our degrees of freedom are not negative, we've addressed that issue of identification. We need to have non-negative degrees of freedom to address the issue of identification. But if we're doing a confirmatory factor analysis model, take that one step further and say your degrees of freedom should be greater than 0. Now, just having positive degrees of freedom isn't enough. There are a couple other issues we need to address to make sure that our model is identified. So another issue is that we need to make sure that we have enough indicators for each factor. If I'm going to extract a factor out of a set of items, I need to have enough items to extract a factor from. And it turns out that what we need is we need to have essentially at least 3 indicators. So if I have a questionnaire with at least 3 items on it, that will work, 3, 4, 5, 6, or any number. But if it's less than 3, then we start having issues here. So if you have at least 3 indicators, then that addresses this issue of we need to have enough indicators for our factor. If you have fewer than 3 indicators, we have a couple options. So for example, if you only have 2 indicators, your model can still be identified if you add an additional constraint that the loadings for both your indicators have to be equal to each other. And if you only have 1 indicator, that could still work if you constrain it to be a perfect indicator with 0 error variance. That is, each item, recall, has our error variance here. And this is a place where if you constrained an item to have 0 variance and to essentially be a perfect indicator with an exact perfect correlation of 1 with the factor, then you could make it work with 1 indicator. In general, I'd say avoid situations where you have less than 3 indicators. There, like I have down here, there are things you can do to work with that situation if by chance you do have fewer than 3 indicators. But the best way to go is simply make sure you have at least 3 indicators. For example, at least 3 items on a questionnaire. Make sure you have at least 3 indicators for every factor you want to estimate in your model. And if you have at least 3 indicators, you will address that second issue that we need to address about having enough indicators for your factors. And then there's a third potential problem or a third issue that we need to address to make sure our model is identified. And this one will require us to take some action. We'll need to do a couple things to make sure this all works out. So this third problem has to do with the fact that we have these 2 latent variables that are not observed, let's say factor 1 and factor 2. If I have a 2-factor model, if I had 1 factor, it'd just be 1 latent variable, or if I had 5 factors, it would be 5 latent variables. But I have these latent variables that are not observed, and each factor is going to have a variance. And how do we decide what that variance should be? If these are not observed variables, how do we scale them? How do we decide how big of a variance they should have? So I've allowed them to have free variance, allowed these variances to be free, to be anything they need to be, but how do we go about deciding what they are? And actually, in this model, that's actually right now, it's kind of a problem because we could say, let's make this variance equal to 2. Let's make it equal to 5. Let's make it equal to 6. We could actually assign different values for that variance and still get the exact same fit for the model. So that's creating an identification problem because we don't know what the variance is. Said differently, we don't know what the scale is. What is it? What are the units that we're using to measure this factor? We don't have a set because it's not directly observed. We don't know what the units are. Therefore, we don't know what its variance is, and that makes it that's creating a problem for having an identified model. To make the model identified, we would need to know some way of what the units are or what the variance is so that we could get the correct solution for the model. So we're going to need to do something about this. We need some way to scale the variance for our latent variables, for our factors. And there's a couple options here, and I'm going to tell you about both of them. And sometimes we might use one, sometimes we might use the other. So I'll tell you about both of them. The most common, the most widely used solution is to do this. We simply take one item for each factor and decide that item is going to be the scaling item and use the scale for this item. So for example, I'll just randomly take x1, my first item for my factor 1, and I'll say x1, and maybe this is a scale measuring depression, and that's a rating of, on a scale of 1 to 5, how much do you feel sad and blue? And so I'm going to take the scale for that item. I'm going to say that scale is what I'm going to use for my factor. However I scale this item will be the same scale I use for my factor, and I will do that by constraining this pathway, this loading, how much factor 1 predicts x1, how much factor 1 predicts that first item. I'm going to constrain that loading to be exactly 1. So rather than leaving that loading free to vary, so originally that was going to be a lambda that was free to be anything it needed to be. And I'm going to say rather than allowing that to be free, I'm going to constrain this pathway and say this pathway has to be exactly 1. And if I constrain that pathway to be 1, what that's doing is saying the scale for my latent variable is going to be the same as a scale for that first item. So I'm going to fix one item from each factor to have a loading of exactly 1. And I'll do that for each factor. So if I have, here's factor 1, and I'll take this first item and constrain that loading to be 1. Here's my second factor. I'll just take the first item on that factor, x4 is my first item loading on factor 2, and I'm going to constrain that lambda to be 1. And it doesn't matter which lambda you use. You could use lambda 1, lambda 2, any one of these. You know, if I wanted to, instead of, for example, instead of constraining x4 to have a loading of 1, I could have let that one be free to vary, and I could constrain lambda 5 to be 1. So I could pick any one of these items that are indicators of a factor and pick it to be the scaling item, the one that I'm going to use to scale my factor with. And it's usually best to take an item that loads pretty well on the factor. So if I have an item that is a very weak loading on a factor, that's probably not a good one to pick to be the scaling item. But oftentimes it works just fine just to randomly take one item. I just take the very first item of each factor is the usual way to do it and set that one to be the scaling item for that factor. So whichever item I pick, that item sets the scale for the factor, and all the other factor loadings that I get are going to be based on how I scaled this first item. The units, if we talk about how these beta weights are going to say, what's the expected increase in x2 given a 1 unit increase in my factor? What does it mean to say there's a 1 unit increase in my factor? Well, that's based on this loading right here. The units of my factor are determined by how well x1 loads in my factor, and that's going to make a difference. So essentially, all my loadings, when I do this, I'm going to have loadings if x1 is 1, if lambda 2 is a stronger loading than lambda 1, it's going to be a value higher than 1. And if lambda 2 is a loading that's weaker than 1, it's going to be less than 1. And so all my loadings are going to be relative to the one that I scaled to be the scaling factor for that factor. Now, that's what happens when we do a confirmatory factor analysis. What we'll see is we're going to get one set of results based on what happens when I scale this according to my item. And then what we'll really want to look at is the standardized results that we get when we turn everything to z-scores prior to analysis based on z-score units. And once I turn everything to z-score units, it won't make a difference. I could pick any of these items and pick it to be the scaling factor, and no matter which one I pick, I will get the exact same standardized results regardless of what I pick. So essentially, this is something that's somewhat inconsequential because in the end, we're really going to be looking at our standardized loadings, the loadings we get when everything z-scores, and when we do that, it doesn't make a difference which item we picked to be our scaling factor. But we need to, this is one way to address the issue. So we need to have a way to scale the variance of our factor, and the most common way to do that is just to randomly pick one item from each factor, usually the first item, and set the lambda, set the factor loading to be, fix it so it's exactly 1. And that will address this issue. Like I said, it won't affect your standardized loadings, will not be affected by this, and it will solve the problem. Note that when we do this, if I take one item for each factor and constrain its lambda to be 1 so that that item becomes a scaling item for the factor, I'm decreasing the number of parameters that we're estimating in the model. I'm no longer estimating lambda 1 because I've constrained that value to be exactly 1. And I'm no longer estimating lambda 4 because now I've constrained that pathway to be exactly 1. So over here is our factor loading matrix, and note that I've changed it just a bit from what I showed you before. Previously, we had x1, x2, and x3, where all 3 of these variables were free to load on factor 1. In other words, when we were telling the computer, when you give us parameter estimates, those parameter estimates can be anything. Whatever works best, estimate the parameter estimate for each of these 3 lambdas and tell us what the best parameter estimate is. And likewise, previously, items 4, 5, and 6 were all free to load on factor 2 and to be anything. They were free to be whatever they wanted to be. But now we've got this loading for x1 on factor 1 is no longer free to be whatever it wants to be. It now has to be exactly 1. And likewise, the loading for item 4 on factor 2, it's no longer free to be whatever it wants to be. It has to be 1. So these are things that the computer is no longer going to estimate when it gives us parameter estimates. It's going to give us back a result that constrains this loading for x1 to be 1, and it constrains the loading for x4 on factor 2 to be exactly 1, and that's what it's going to be because that's what we fixed it to be. So when we do this, when we set the scale for our factor by identifying items to be scaling items, and we set the lambda for those items to be 1, that means we're reducing the number of parameters that we're estimating in our model. So putting all that together, it means we have gained 2 degrees of freedom. So here is the slide showing the calculations we can do for determining degrees of freedom. And so now we have 13 free parameters. This one, x1 on factor 1, that's no longer free. That's now set to be 1. x1 on factor 2, that's no longer free. So now if we count up all the times we have the word free on this page and count up all the free parameters, we have 13 free parameters. And as before, we calculated a while ago, we saw that we had 21 elements in our variance-covariance matrix. So now if I take 21 minus 13, we see our degrees of freedom are 8. So before I fixed these to be 1, we had only 6 degrees of freedom, but now I fixed these 2 parameters to be 1, and now our degrees of freedom went up to 8. So now we have a model with 8 degrees of freedom. So we've been looking at the issue for identification that our factors need to be scaled somehow. We need some way of scaling what our factor scores are. And we need to do that in order to have an identified model. And we were just looking at one option for addressing that issue was to constrain one item on each factor to be a scaling item and constrain that item to have a loading of exactly 1 on the factor. And that is one way to address the issue to make sure that our factor is scaled in a way that will make sure our model is identified, that our factor will have a defined scale for it. Another way that we can address the same issue that actually works equally as well, and depending on the situation, sometimes it's more convenient to do one solution or the other, but an alternate thing we can do, an alternate solution to that same problem, and this might seem more intuitively obvious, we can just simply fix the variance for our factor to be something. Most obviously, or the most logical thing to do is just to fix that variance to be 1, like we would do for a standardized solution. Just fix our variance of each factor to have a variance of exactly 1. So fix our factor variances to equal 1. And once again, this is not going to change our standardized loading. So if you were to do either of these, you could do the option of you could constrain a lambda loading for each factor to be 1, or you could constrain the variance of each factor to be 1. Either way, once we go on and calculate the completely standardized solution where we get a solution where everything's been turned to z-scores, we're going to get the exact same results. Eventually we'll be looking at things like fit. We can also calculate degrees of freedom. We'll see that in just a moment here. Our factor loadings, everything will be identical regardless of which solution you use. Sometimes the option of constraining lambda loadings is easier to use. That's probably the more common one to do, but sometimes it works a little better just to fix your variances for your factors to be 1. Although in general, it really doesn't make a difference either way, because we're going to get the same solution. No matter which option you choose, we're going to get the same solution. And it will have the same degrees of freedom, because note that in this case now, instead of constraining a lambda loading to be 1, we're now constraining a variance to be 1. But in either case, we're putting a constraint on the model. So it's a matter of, do you want to put the constraint here or put the constraint there? Do you want to put the constraint on lambda 4, or do you want to put it on the variance for factor 2? Either way, we're putting a constraint on the model. Either way, we're putting the exact same number of constraints. So if I have 2 factors, I'm putting 2 constraints, either constraining 2 lambdas to be 1 or constraining 2 variances to be 1. So either way, I'm adding 2 constraints. Either way, I'm going to add 2 degrees of freedom. So my degrees of freedom will be the same regardless of which option I choose. So now we're ready to go ahead and test our confirmatory factor analysis model. This will involve getting parameter estimates for all the parameters that we're free to vary, and then testing the fit of our model. And the process of doing this will be the same process that we talked about in a previous unit when we talked about doing structural equation modeling. In a previous unit, we talked about doing structural equation modeling for testing regression equations, and we'll do that same process here. And recall how that went. First, we calculated parameter estimates, or we got parameter estimates for our model, and then we used those parameter estimates to create this reconstructed variance-covariance matrix. And then we compared the reconstructed variance-covariance matrix with the actual observed sample variance-covariance matrix. And the process of identifying parameter estimates for our model was a process of determining which parameter estimates would produce a reconstructed variance-covariance matrix that came as close as it possibly could to the actual sample variance-covariance matrix. So we're going to do the same thing here. So if we were to test this confirmatory factor analysis model that we're looking at on this page, let's look at the parameter estimates we would get. We would get 6 lambda loadings, 1 for each of our items. So we'd have 6 lambda loadings, and we'd have 6 error variances, 1 for each item. And we would have a correlation between our 2 factors. And then we would either have to constrain one of our loadings for each factor to be 1, or constrain our variance. Let's say we constrained our variances to be 1. So if we did that, that's not a parameter estimate if we constrain that to be 1. So we're going to estimate these estimates here. So we've got 6 error variances, 6 lambdas, and this correlation. So we're going to estimate all these parameters are going to be estimated in our model. And then we'll need to be able to take a way to take all these parameter estimates and use the estimates for these parameters to recreate a reconstructed variance-covariance matrix. So we'll need a way to say, once we've estimated our model, we've got our estimates for all of our error variances, we've got our estimates for our lambdas, we've got our estimate for the correlation between factors. Once we have all those parameter estimates, we'll need to be able to take those parameter estimates, plug them into a formula, and get a reconstructed variance-covariance matrix. And again, as before, the process of determining what our parameter estimates are is a process of figuring out which parameter estimates will reproduce a reconstructed variance-covariance matrix that will come as close as it possibly can to the actual observed sample matrix. And I'm not going to go through all the equations that we would use to reconstruct the variance-covariance matrix for our confirmatory factor analysis model. But there is one equation, probably the most widely used equation, that we would need that I do want you to be familiar with here. And so let's say we want to know what is the covariance between x1 and x2. So note that our covariance matrix that we're working with here will be a 6 by 6 matrix. We have 6 items, 6 variables in our study. So if we have a questionnaire with 6 items on it, and we're doing a confirmatory factor analysis on our 6-item questionnaire, it means we have 6 items, 6 variables. So we will have 6 rows and 6 columns in our variance-covariance matrix. And one of those cells will be the covariance between x1 and x2. We'll have covariance between x1 and x2, between x2 and x3, between x1 and x3, x1 and x4, x1 and x5, and so forth. But so for right now, let's just focus on how would we estimate the covariance between x1 and x2. So if we have all of our parameter estimates to estimate the covariance between x1 and x2, all we need to know the lambda loading for x1, the lambda loading for x2, and we need to know the variance for our factor. And it's possible we've constrained one of these things to be 1, and if so, that would just be entered into our formula when we calculate this. And the formula is simply this. We take the loading for lambda 1 times the loading for lambda 2 times the variance for our factor. In other words, we just multiply those together. So the product of our 2-factor loading times the factor variance will actually give us the estimated covariance between x1 and x2 in our reconstructed variance-covariance matrix. And we would actually use that same procedure, for example, to get the covariance between x1 and x3 or x1 and x2. Any 2 items that are on the same factor, this formula will work. And so that gives you an example, and it would be good to be able to plug that in and know how that works to get a general sense of the idea that once we have our parameter estimates, for example, we know our lambda loadings, we know our factor variance, and so forth. Once we have our parameter estimates, we can use our parameter estimates to reconstruct the variance-covariance matrix. In this case, we can use the lambdas of lambda 1, lambda 2, and our factor variance to estimate or reconstruct the covariance between item x1 and item x2. And in that way, we could go through, and there would be formulas for everything for an entire variance-covariance matrix, and we can use the parameter estimates from our model to reconstruct the variance-covariance matrix. And as in our previous unit when we talked about structural equation modeling, this means we will end up with 2 variance-covariance matrices. We will have our reconstructed variance-covariance matrix, the one that we calculated based on our parameter estimates, and we're going to call that sigma, use the Greek letter sigma to indicate that matrix. And we will have our sample variance-covariance matrix, the actual variance-covariance matrix that we got from our actual data set that we will indicate with the capital S. And each of these matrices will have a square matrix with number of rows that is equal to number of items, number of columns equal to number of items. So if I have a 6-item questionnaire, it'll be a matrix with 6 rows and 6 columns. We'll have 1 variance for each item, and then we'll have all the possible covariances between all the possible pairings of our items are all put together in this matrix. And so we'll have our sample variance-covariance matrix, our reconstructed variance-covariance matrix, and again, the process is going to involve identifying what parameter estimates will make this reconstructed variance-covariance matrix, which again, back up a previous slide, we reconstructed that matrix using formulas like this one right here to reproduce the covariances and variances in our matrix based on our parameter estimates. So I use equations like that, reconstruct the variance-covariance matrix, and then we want to identify what parameter estimates will produce a sigma, a reconstructed variance-covariance matrix, that comes as close as it possibly can to the actual sample variance-covariance matrix. So that leads to the question, what formula should we use to decide how close our reconstructed variance-covariance matrix comes to the actual sample variance-covariance matrix? Previously, we talked about the maximum likelihood formula, and I'm going to talk about that again shortly. There's also some other ways that we can do that, but one way or another, we need to have some kind of formula that we can use to determine how close does our reconstructed variance-covariance matrix sigma, how close does it come to S, our actual sample variance-covariance matrix? What is the size of difference between S and sigma? Because in estimating parameter estimates, we want to minimize this difference between S and sigma. We want to make the difference between these two matrices as small as possible. And they're actually, in addition to maximum likelihood, which again I'll mention that in a moment, but there's actually a few different formulas that we can use to determine the size of difference between S and sigma. And whatever formula we use, I want to mention that we're going to call that formula that we use, we're going to call that a fit function or an estimator. So when you're doing structural equation modeling, someone might say, oh, which estimator are you using? In other words, or they might say, what fit function are you using? And what that question is, it's a question of what formula are you using to decide how big the difference is between S and sigma. And maximum likelihood, which we talked about before, I'll mention that just shortly here, is one type of fit function. Maximum likelihood is one estimator. It's a formula that we could use to measure the difference between S and sigma. And that's one approach. There's actually going to be a few different approaches we will look at as we go along here. But note that whatever formula we use to determine the size of difference between S and sigma, we're going to call that formula our fit function. Or another term, we could call that our estimator. And there's a few different fit functions or estimators we can use, but again, they're all going to involve measuring the difference between our S, our sample actual observed variance-covariance matrix, and sigma, our reconstructed variance-covariance matrix. Now, this slide is just summarizing some things that we've already been talking about, and that is the fact that when we do confirmatory factor analysis, or actually any type of structural equation modeling, when we run our models, part of what we're doing is we want to get parameter estimates. We'll have a set of parameters that are free to vary, and we want to get our estimates for all those free parameters. And the process of calculating those estimates could be called the process of estimation. So how do we go about doing estimation? How do we get those parameter estimates? And as I mentioned before, we get those parameter estimates by figuring out which parameters will produce a reconstructed variance-covariance matrix that comes as close as possible to the actual observed sample variance-covariance matrix, and that is measured by our fit function, our estimator. So we'll have a formula that will calculate fit, our estimation function, our fit function, and we'll use that formula to measure the size of difference between S and sigma, and then we want to figure out what free parameters can we plug in that will minimize our fit function, that will make the fit as good as possible as defined by the formula we're using to define fit. So we want to minimize our fit function. What parameters, what estimates can we produce for each of our parameters that will minimize, that when taken together, will produce the smallest possible fit function? In other words, what parameter estimates will make our reconstructed variance-covariance matrix come as close as possible to our actual observed sample variance-covariance matrix. So probably the most widely used fit function, or estimator, is maximum likelihood. So maximum likelihood is a type of fit function. It is an estimator. It gives us an equation that we can use to evaluate the size of difference between S and sigma, our sample variance-covariance matrix, and the reconstructed variance-covariance matrix. And we already talked about maximum likelihood in our previous unit when we were using structural equation modeling to get estimates for regression models. I talked about using maximum likelihood then. And a lot of computer programs for doing structural equation modeling make maximum likelihood their default. So if you just don't specify anything, it might just assume you want to use the maximum likelihood estimator to get your parameter estimates. And as we talked about before, maximum likelihood is a formula, and when we plug it in, it's going to give us a value that indicates the likelihood of obtaining the actual sample variance-covariance matrix that we got. What's the likelihood that we would get that if sigma, our reconstructed matrix, is actually giving us the true population parameters? So if our sigma matrix, if our model and the parameter estimates in our model. If our model is actually showing us the true population parameters, if that's true, what is the likelihood that we would get the actual variance-covariance matrix we got in our sample? What is the likelihood of our results in our sample if our model parameters are actually giving us the true population parameters? So again, maximum likelihood is a formula, provides a value that indicates the likelihood of obtaining S, our sample variance-covariance matrix, if sigma, our reconstructed variance-covariance matrix, is actually the true set of population parameters. And down here I have the formula for maximum likelihood. I'm not going to actually ask you anything about that formula. If you're familiar with matrix algebra, you can look and see that we're getting, it's giving us a difference between S and sigma, and that's getting plugged into that equation. So you can just trust me that that's what that formula is doing. And the key thing is to note that all the maximum likelihood will be one type of fit function. I'm going to talk about another type in just a moment here. But all fit functions, all estimators in one way or another are going to be giving us some measure of what's the size of difference between S and sigma, the difference between our sample variance-covariance matrix and sigma, our reconstructed. And this formula down here, this formula for maximum likelihood, is one approach to measuring that difference. And when you plug that formula in, you get the value that indicates the likelihood of obtaining S if sigma is the true population parameter. You may have noticed that on the previous slide, I had a statement there that said maximum likelihood works best with continuous items. What exactly do I mean by that? Let's take a closer look at this issue. So say, for example, I wanted to assess how much people like potatoes. So maybe I have an item on a questionnaire that goes like this. I have the statement, I like potatoes, and I have people rate that on a 3-point scale. 1, not at all true. 2 is somewhat true. 3 is extremely true. And if we think about levels of measurement, we could describe the scale as an ordinal scale. We have just 3 different levels, and we know that 1 is less than 2 and 2 is less than 3, but we don't necessarily have equal distances between a 1 and a 2 or between a 2 and a 3. So we could call this an ordinal scale. Another term we could use is we could say it is a discrete scale. So we could call it ordinal or discrete, 2 different ways of describing the same thing. So this option with a discrete scale with just 3 levels is different than, say, if we assumed the potato liking was continuous. So maybe here I have my normal curve over here. Maybe potato liking is something that's a continuous variable that follows a normal curve, and with a continuous item, there's an infinite number of possible levels at which you could like potatoes. Someone could like potatoes way up here or down here on a normal curve. There's an infinite number of, along this normal curve, along this x-axis, there's an infinite number of points along that axis. So if we take any 2 points, say someone likes potatoes this much or this much, any 2 points, we could always divide that in half, and there could be someone right in the middle between those 2 points. And if we divide that in half, there could be someone in the middle between those 2 points, and so forth. So there's an infinite number of points along this continuous scale. And so potato liking could be something that's continuous, where there's an infinite number of different levels at which you might like potatoes. Or we could measure potato liking on a discrete or ordinal scale, in this case where we have just 3 levels. Now in psychology, just about everything we measure is probably measured at an ordinal level. It's very difficult to get a scale that is truly continuous. There aren't that many things we can measure that truly have an infinite number of possible levels that people could score at. But we can talk about variables in terms of how many levels are there. So for example, here I have an item that has just 3 levels. Maybe instead of having 3 levels, I could rate this at 5 levels, or 7 different options. Maybe I could have 7 response options, or maybe have strongly agree, agree a little bit, neither agree nor disagree, somewhat disagree, disagree, strongly disagree, or something. So could I have several levels here? Or maybe I have, if I move from an item to an actual instrument like a scale that has several items on it, where I sum items together, maybe I have a scale comprised of 20 different items on it, or 8 items, and I sum those together. Now when I create a scale by adding items together, I'm going to have more and more levels that I'm measuring my variable at. So essentially what we have here is a situation where we can have some items that have very few levels, and they're very clearly categorical. And then we can add more and more levels to our items, and as we measure something with more and more levels to it, it approaches something more and more that's like continuous. In truth, we're probably never going to get something that's actually continuous, but the more levels we measure something with, the more it becomes like continuous. And essentially, what I'm saying about maximum likelihood is that it works best the more you're measuring something that comes close to being continuous, that has enough levels to it that it is somewhat kind of like being continuous, then that can work well for maximum likelihood. If you have just 3 levels to it like this, if I have an item with just 3 levels, this isn't going to work very well for maximum likelihood. Now, the point where maximum likelihood works well is hard to tell. There's actually studies that have tried to find that, and it's a rather complex issue, and there's really no cut and dry answer. But I'd say in general, if you only have like 5 items, 5 levels to an item, that's probably going to be problematic for maximum likelihood. If you're at 8 levels, 8, 9, 10 levels, that might be okay. If you've got more than 10 levels, that's probably definitely going to be okay for maximum likelihood. But most of the time, we're using questionnaires. If I'm doing confirmatory factor analysis, usually I'm doing it with items on a questionnaire, and usually those items only have maybe 5 levels to them, and that's going to be somewhat problematic for maximum likelihood. That's not quite enough levels to make maximum likelihood work really well. So maximum likelihood works best with continuous items. And if I'm doing a study where I have variables that are scores on a scale, if I'm doing structural equation modeling and I have a measure, say a 15-item depression scale, and I'm using my depression scale to predict a 20-item childhood trauma scale or something like that, that if I'm using scaled scores that have many items to it, that's probably not going to be a problem. But if I'm doing confirmatory factor analysis and I've got individual items and each item is comprised of only just a few levels, maybe 3, 4, 5, 6, 7 levels to it, we're going to have some problems with maximum likelihood. It's not going to work as well as it could if our items were closer to continuous. So what can we do about that? So the solution will involve using a different estimator, that is, using a different fit function. And to talk about the fit function I want to use, I want to first give an overview of a general type of fit function called a least squares method. There's actually several different fit functions that involve a least squares method for the fit function. So we have several different types of least squares methods for fit function calculation. So first I want to give you an overview of what is, in general, least squares methods for estimating a fit function. And then I'm going to talk about one specific type of least squares method that will work very well for ordinal items. So if I have a questionnaire and my questionnaire is comprised of items, each item is rated on a scale, maybe it's a 5-point scale or a 7-point scale, I'm going to talk about a method that will work very well for dealing with those types of items, which is, if you're doing confirmatory factor analysis, more often than not, you're probably doing it with a questionnaire that has ordinal items. So this will be very important for doing confirmatory factor analysis with questionnaires. So as I mentioned, there's several types of approaches that we can use for a least squares method for our estimator, for our fit function. And in general, all these formulas are going to involve 2 components. And one component will be, we're going to estimate squared residuals. We're going to take our actual observed sample variance covariance matrix and our reconstructed matrix and just take each value from the observed minus the value from our reconstructed to get a residual and square it. If you recall, when we were doing exploratory factor analysis, we had a reconstructed correlation matrix, and we compared our reconstructed correlation matrix to the actual observed correlation matrix, and then we calculated squared residuals. And this would be the exact same thing here, where we just look at the difference between each cell in our variance covariance matrix and take the value we get in our S matrix, our actual observed matrix, minus the value we have in our sigma matrix, and get the residual and square it, and get those squared residuals. And So essentially, a least squares method is going to try to minimize the size of those squared residuals. But a least squares method is also going to add one other thing. It's going to look at each of those residuals, each of those components in our variance-covariance matrix, that is each variance and each covariance, and it's going to make a decision about what is the standard error of that element. So if I'm looking at a covariance between two items, what is the standard error of that covariance? That, and recall that a standard error is dealing with sampling error. That is, if we do our study over and over and over again, how much will our observed parameter estimate typically deviate from the actual population parameter? So if I were to do a study, calculate a covariance between two items, and then replicate that study and recalculate that covariance, and then replicate my study, recalculate that covariance, and do that over and over again, how much will the covariances from all my studies typically deviate from the true population parameter? That would be the standard error of my covariance. And so what I want to do is I want to look at all the elements, the covariances and also the variances in my variance-covariance matrix, and calculate these standard errors to determine how well I can estimate what they are. And then I'm going to use these standard errors to weight my residuals. In other words, if I have parts of my matrix that I can estimate with a high degree of accuracy that have very small standard errors, then I'm going to give those residuals more weight when I add everything up. I'm going to give the residuals that have small standard errors are going to carry more weight. And if I have residuals based on covariances that have big standard errors, they're going to get less weight. So I'm going to calculate my residuals and then calculate this matrix that includes these standard errors for all the elements in S, all the elements in my variance-covariance matrix. I'm going to estimate the standard errors for each element, and I'm going to call this matrix of standard errors my W matrix, which stands for weight. It's my weight matrix. And I'm going to weight these residuals that I get by W, so that if I get a residual for a covariance that has a small standard error, a covariance that I can estimate with a high degree of precision, then I'm going to weight that residual. I'm going to give that residual more weight when I add things up. If I have a covariance between two variables that have a very large standard error that I can't estimate very precisely, then I'm going to give that residual for that covariance. I'm going to give that less weight because I can't estimate that as precisely. So I'm going to estimate these residuals. Then I'm also going to estimate this W matrix, which gives me the standard errors for all the elements in my S matrix. And I'm going to weight these residuals by the standard errors so that residuals based on a covariance that I can estimate with high precision gets more weight, and residuals based on a covariance that I estimate with poor precision gets less weight. And so it's basically a process of I'm going to calculate these residuals, difference between S and sigma, and I'm going to weight my residuals by this W matrix, which is based on the standard errors of the elements in my variance-covariance matrix. Now I have a note at the bottom here that as it turns out that we're going to talk about a specific type of least squares method in just a moment here. And as I said, there's several different types. One thing that's common across all the different least squares approaches is that as your sample gets larger, usually your results get more and more similar to a maximum likelihood result. So if you had, say, 1,000 or several thousand people in a sample, if you're using one of these least squares methods, it would probably be almost the same as maximum likelihood. So most least squares methods become more and more similar to maximum likelihood as your sample size increases. So this is in general what a least squares approach did. So if we're doing a least squares approach, we need to calculate residuals, and then we need some way to calculate this W matrix, and that's going to be the basic elements of doing a least squares approach. Now I want to talk about a specific type of doing a least squares fit function that's called diagonally weighted least squares. Diagonally weighted least squares, or DWLS, is one type of fit function or one type of estimator that uses that least squares method. Now, there's actually several different names for this approach, and different software packages and different programs call it slightly different things. So diagonally weighted least squares is essentially the same thing as what's sometimes called weighted least squares mean and variance adjusted, which is essentially the same thing as robust weighted least squares. So robust weighted least squares mean and variance adjusted, or WLS-MV, or diagonally weighted least squares, DWLS, are actually different terms for essentially the same thing. There's actually some very minor differences between some of these things, and different software packages approach things just a little bit differently. But for all practical purposes, these are essentially all different terms for the same thing. And these are all different types of using the least squares method as the fit function, as the estimator. And this particular approach works very well with ordinal items. So if you have a questionnaire with items on it, and each item is rated on, say, a 5-point scale or a 3-point scale or a 7-point scale, this method works very well for that. It gets kind of complex, but I think it's worth going through, because if you're doing confirmatory factor analysis, more often than not, you're probably doing confirmatory factor analysis with questionnaire items, and questionnaire items usually only have 7 or fewer levels to them, and usually they function as ordinal items. So this is usually the best approach to use, and certainly if you're doing confirmatory factor analysis with a questionnaire and you only have 5 or 7 levels per item, this would be the ideal approach to use, is to use this diagonally weighted least squares. So let's look at what this approach involves. It's going to involve, as we'll see in a moment here, we'll need to calculate something called thresholds, and then we're going to need to calculate something called polychoric correlations, and then we're going to need to calculate something called an asymptotic covariance matrix. So I've got 3 different steps we're going to need to go through here. So let's take a look at what those steps are to do this diagonally weighted least squares solution that will give us the best possible estimator if we're working with ordinal items, as we probably would be if we're doing a confirmatory factor analysis with a questionnaire. So as I mentioned, diagonally weighted least squares, we're going to need to calculate thresholds, and then something called polychoric correlations, and then this thing called an asymptotic covariance matrix. Let's start, as the giraffe is thinking over here, what are thresholds? What is that all about? So the first step to calculating thresholds, and this is actually the basic assumption that underlies everything we're doing when we're doing diagonally weighted least squares, is we're going to assume that whatever we're trying to measure, that the underlying construct is continuous. So for example, if I was wanting to measure how much people like potatoes, and I had say an item on a questionnaire that says potatoes are fabulous, and you could say I agree strongly, agree, undecided, disagree, or disagree strongly. So I have 5 levels, 1, 2, 3, 4, 5. So I have a questionnaire item with just 5 levels on it. But what I'm going to do is I'm going to assume that although my questionnaire item only has 5 items, I'm going to assume that the underlying construct, say in this case how much you like potatoes, that it actually is a continuous variable, and also that it's normally distributed, so that potato liking actually fits this normal bell-shaped curve. It's continuous, and there's all these infinite number of levels at which people could like potatoes. Most people are in the middle. As you go further and further away from that middle, you get fewer and fewer people. So I'm going to assume that the actual construct, so I'm going to assume that the underlying construct, the real thing, potato liking, that I really want to measure, I'm going to assume that that construct fits a normal distribution. And I'm going to assume that when I give this questionnaire item that only has 5 levels on it, I'm going to assume that what I'm doing is discretizing, I can say discretized, or I'm not sure if it's discretized or discretized. I think it's discretized. Anyway, I haven't heard that word pronounced too much. A nice fancy word you can use when you want to impress people. So discretized, what I mean by that is to take something that's continuous and to chop it up into discrete categories. So if I have a continuously distributed item that has an infinite number of levels at which you can like potatoes, and I take that continuous item that has an infinite number of levels, and I chop it into discrete categories, or into ordinal categories, in this case a 1, 2, 3, or 4, or 5, I can say I'm discretizing that item. I've taken something that's continuous and I've discretized it into an ordinal item. And when we do diagonally weighted least squares, the basic assumption here is that that's what has happened. We're going to assume that I was trying to measure something that in the real world was that it actually existed as a continuous construct, that the construct itself is continuous. There's an infinite number of levels that people could experience whatever it is I'm trying to measure. So if it's potato liking, I assume in the real world there's an infinite number of levels at which people could like potatoes. The potato liking is a continuous variable, and that my questionnaire item has discretized it. My questionnaire item has artificially divided this continuous construct into 5 discrete categories. It's made it ordinal. And then I'm going to assume that when I do this, my response options represent different sections underneath this normal distribution. Now they could be different, I have of unknown size, so they could be different levels. So it might be that strongly disagree is a fairly small section, disagree might be a little bit bigger. Here I have undecided, maybe not too many people pick that, maybe agree strong, maybe there's a lot of people pick agree strongly. So these are not evenly dispersed sections, are not of equal size. I don't really know what the size is, but I assume basically here that somewhere we could chop it off and say that if you're responding 1, you're at this point of the curve. People that gave a 2 are in this area. People that gave a 3 are in this area, and so forth. So I assume that I've chopped my normal distribution into these 5 sections, and that each section represents a different response option from my questionnaire. So now, with that basic assumption, we're ready to calculate thresholds. So thresholds are going to be the cut points between response options if we assume a normal distribution and use a z-score unit for labeling our scale. So if we assume a normal distribution and label everything with z-scores, what are the cut points between each response option? This is going to be very similar to something we did early on in this class when we normalized scores, when we took someone's score on an instrument and said, well, what would this person's score be if we assume that the underlying construct fits a normal distribution? And if you recall, we took that person's score and we turned it into a percentile, and then we said, well, if someone is at, say, the 25th percentile, what would that person's z-score be at the 25th percentile if data are normally distributed? And this is the same type of thing that we can take we can look at the data in our study and say what percent of people chose disagree strongly, what percent of people chose number 2, what percent of people chose number 3, and then we can say, well, if data are normally distributed, what's our best guess for what the cut point would be on a normal distribution between scoring a 1 and scoring a 2? And what's our best guess for what the cut point would be between a 2 and a 3? And those cut points will be our thresholds. So we're going to estimate these cut points between the response options, and we're going to label these using a z-score scale with a mean of 0, standard deviation of 1. We're going to use that z-score scale to label our cut points, which will be our thresholds. And note that if we have, say, a 5-item scale, then to break apart these 5 categories, we need 4 thresholds. So we'll have the number of thresholds will always be 1 less than the number of levels for our scale. So we will estimate our thresholds, which are the cut points between response options on the normal distribution that we would assume we would get, estimating based on our sample the percent of people scoring each response option, trying to guess where these cut points would be on the normal distribution of what things would be like in the real world if the thing we're measuring is truly continuous, and if it actually fits a normal distribution, then based on our scale items, what's our best guess for where these cut points or these thresholds fall. Then once we've calculated thresholds, the next step will be to calculate something called polychoric correlations. And as our friendly giraffe is wondering, the next question is, so what are polychoric correlations? So say I had 2 items on a questionnaire. Maybe I had item X1 and item X2. And maybe X1 was, maybe I was measuring how much people like potatoes, and X1 was rate the extent you agree how much do you agree with the statement, potatoes are wonderful. and maybe x2 is I would like to be a potato farmer or something like that. So we have two items measuring how much people like potatoes, and I want to calculate the correlation between x1 and x2. So I want to calculate the correlation between item 1, I like potatoes, and item 2, I want to be a potato farmer. What is the correlation between these two items? And we're going to calculate something called a polychoric correlation, which is going to be essentially the correlation that we would estimate between these two items if the items weren't discretized. So we're going to assume that because we've taken a continuous variable and chopped it into categories, that's going to make our observed correlation a little bit smaller than the true correlation of what we would have gotten if we hadn't discretized our items into these artificial categories. So a polychoric correlation is going to be a way of estimating what is the correlation between these two constructs or these two items if we actually were able to measure them as continuous variables and hadn't had to discretize them. So that's what we're going to do. And we're going to assume that each item was measured on a normal distribution, and we've estimated our thresholds here. So I'll estimate the thresholds for item 1, and I'll estimate the thresholds for item 2. And then I'm going to create this contingency table, or a crosstab table, where I'll just note how many people, so here I have how many people said agree strongly here and disagree strongly there. There are actually 0 people gave that. How many people said, say, for example, agree and disagree there? There were 6 people there. How many people said agree and undecided? There were 7 people here. So I'm just making a contingency table. How many people in each cell? So there were 9 people that were undecided on x2, but agreed strongly to x1. And I'll just make this contingency table showing how many people appeared in each cell. I have a note at the bottom here that when we do this, this is going to be our first step for calculating this polychoric correlation between x1 and x2. And we have some cells that have 0. There's 0 cases in these cells, and that will make the calculations a little bit more complex. It'll make some problems that can be dealt with, but they make the calculations a little more complex. And just to mention that here because a lot of times if you're doing a confirmatory factor analysis and using this procedure, when you have cells with zeros in them, you might get warning messages. This would be true, for example, if you're using R and using the Levan program for doing your structural equation models, for doing your confirmatory factor analysis. It's very common to have, unless you have a huge sample, it's very common to have cells with zeros in them. And when that happens, you're probably going to get warning messages, and those are warning messages that you really don't need to worry too much about. It's just telling you you had cells with zeros. That made our calculations a little more complex. We're just letting you know we had to work harder to calculate these things because you had zeros in these cells. But more often than not, you're going to have zeros in your cells, so you'll usually get those warning messages. So we've got our contingency table. We've taken our items on x1 and x2. We've identified the thresholds for each item, and then we've plugged in this contingency table. And now we're ready for the next step. And for this next step, I'm going to take something that's actually incredibly complex and explain it away with one very broad brushstroke here, and simply say what we're going to do now that we have our 2 items. We want to get the estimated correlation between x1 and x2, assuming that x1 and x2 actually measure continuous constructs that we've discretized. And I want to get the estimated correlation between these 2 variables. And the polychoric correlation, what I'm going to do is I'm going to estimate what population correlation between 2 continuous variables when discretized at these particular thresholds that I've estimated right here. So what population correlation between 2 variables discretized with these particular thresholds is most likely to reproduce this particular contingency table. And the formulas and iterations for doing that get rather complex, but if you think about what we've been talking about with structural equation modeling, it makes sense that we can estimate these things. We can figure out, okay, there's formulas we could use to say what population correlation matrix between 2 continuous variables, given the way we've discretized these variables, is likely to reproduce this contingency table. So we could figure out if we've discretized these 2 variables at these levels and say that true population correlation was 0.3. If it was supposed to be 0.3, how likely is it to get this particular contingency table if we discretize these variables at these levels, how likely are we to get this particular contingency table if the true population correlation, say, was 0.3? What about 0.4? If the true population was 0.4 and we've discretized these variables at these particular levels, how likely is it to get that particular contingency table? Or what if the true population correlation is, say, 0.6? And we've discretized these variables at these particular levels, how likely is it to get this particular contingency table? And so we can explore some different possible correlations and find what correlation makes this contingency table most likely. What correlation best reproduces this contingency table? And once we identify that correlation, once we identify the population correlation that when discretized is most likely to produce this contingency table, that is our polychoric correlation. That is the estimated correlation if the variables had not been discretized. So putting things together, the second step in estimating diagonally weighted least squares is to calculate a polychoric correlation matrix. That is, we want to get the polychoric correlation between all the possible pairs of the items on our assessment instrument. So for example, if I have a really short assessment instrument, I have, say, just 3 items on it, maybe just 3 items regarding how much people like potatoes. Maybe I like potatoes, I want to be a potato farmer, I think potatoes are fabulous, maybe those are my 3 items, and I want to estimate the polychoric correlation matrix. And so there's going to be a correlation matrix. I'll have 1s on the diagonal, as I would on any correlation matrix. And then here I have what's the correlation between item 1 and item 2? What's the correlation between item 1 and item 3? What's the correlation between item 2 and item 3? And if I just have 3 items, that's fairly simple. I just have those 3 correlations. And the thing is, I'm going to estimate, these aren't going to be the normal Pearson correlations that we would typically calculate where I take a covariance divided by the product of my 2 standard deviations. Instead, it's going to be this polychoric correlation matrix where I go through all those complex steps of estimating my thresholds and then estimating my contingency table and then identifying what correlation is most likely to reproduce this contingency table with these discretized levels, and that is my polychoric correlation. So I do that for the correlation between item 1 and item 2. I do that for the correlation between item 1 and item 3, do that for the correlation between item 2 and 3, and however many items I have on my questionnaire, I do that for all my possible pairs of items, and then I can get this correlation table, which is now my correlation table of polychoric correlations. It's the table of correlations that I'm estimating would be the true correlations I would get if I hadn't discretized my items and if I were actually measuring things as continuous items and they really were continuous and I was measuring them that way. What would my correlations be? So the polychoric correlation matrix estimates that. And the final thing we need to calculate diagonally weighted least squares is to calculate this thing called an asymptotic covariance matrix. And again, as the giraffe is wondering, what is an asymptotic covariance matrix? So to describe what an asymptotic covariance matrix is, let's first imagine that we do a study where, say, we just have 3 items on a questionnaire. That will make things easier here. A very short questionnaire with just 3 items. And say we do our study, and we have 3 items, and we calculate a polychoric correlation matrix. We get the correlation between item 1 and item 2, between item 1 and item 3, and between item 2 and item 3. And we get this polychoric correlation matrix right here, this very first row at the very top here. Maybe that's a study I do, and I get this polychoric correlation matrix between all the items on my questionnaire. In this case, I only have 3 items, so it's a fairly small matrix. Usually I'd have more items, and it would be a much bigger matrix. But I get the matrix from my study. And now I'm going to do that thing I sometimes say where let's imagine that I replicate my study over and over again. So this first row was the first time I do my study, and I get this polychoric correlation matrix. And then I replicate my study. Let's collect another sample, do it all again, and get a different, and it'll be slightly different because each time I do my study, I'm likely to get slightly different results. So I get this polychoric correlation matrix. And then I replicate my study again and get another polychoric correlation matrix. And then I replicate my study again and get another one, and so forth. I was trying to make these smaller and smaller, kind of give the feel of I'm doing like kind of an echo, replicate, and over and over and over again, an infinite number of times. And each time I calculate my polychoric correlation matrix between all the items on my questionnaire or on my assessment instrument. And note that what I'm talking about here is sampling error. Previously in this class and other classes, I often bring up this googly-eyed sheep table to talk about different types of distributions. One type of distribution is the distribution of sampling error. That's if I replicate a study over and over and over again, how much do statistics from different samples typically deviate from the true population parameter. That's an estimate of sampling error. And that's what I'm talking about here. If I'm going to do a study over and over again, calculate a polychoric correlation matrix, and then replicate my study, calculate another polychoric correlation matrix, and replicate that over and over and over again, I can see how much the different, in this case, how much the different polychoric correlation matrices from different samples deviate from what would be the true population parameter polychoric correlation matrix. So if I'm replicating my study over and over and over again, I'm looking at sampling error. In this case, how much do polychoric correlation matrices from different samples deviate from the true population parameter polychoric correlation matrix would be the key question we can address with this. And this is a question of sampling error. Now, usually when we've talked about sampling error in the past, we've talked about sampling error for just one single statistic at a time. For example, if we want to talk about sampling error for calculating a mean, we indicate that with the standard error of the mean. That is, if I do a study, calculate the mean, replicate my study, calculate the mean again, replicate my study, calculate the mean again, and get all the means from all my studies. If I replicate my study over and over and over again an infinite number of times, I get all those means from all my studies. I can then calculate a standard deviation. How far do my means typically deviate from the true population parameter? How far do the means from my individual studies typically deviate from the true population parameter mean? And that is the standard error of the mean. But now, talking about sampling error, things are a little more complex because I'm not talking about sampling error for just a single statistic, but I'm talking about sampling error for an entire polychoric correlation table. So I do a study and I calculate an entire polychoric correlation matrix, and I replicate my study and I calculate once again a polychoric correlation matrix, and I'm doing that over and over again. So I can't talk about sampling error for a single statistic because I have an entire matrix of correlations I'm working with. So that's going to make things more complex. And here is what we're going to do. So imagine I do my study the first time, and I do my study, and say I have a questionnaire with just 3 items on it. Usually we have questionnaires that are longer, but for this example, let's make it a nice short questionnaire. So if I have just 3 items, I have just 3 correlations, 3 polychoric correlations to estimate. The correlation between item 1 and item 2, the correlation between item 1 and item 3, and the correlation between item 2 and item 3. And I could plug that into my polychoric correlation table here. I just plug those values in, 1, 2, 1, 3, and 2, 3. Just plug that into my table there. And I'm not going to care so much about the diagonal, the ones on the diagonal, because in a correlation table, you will always have ones on the diagonal. So I'm going to focus on the actual correlations in my table. And what I'm going to do now is I'm going to make a data set, and I'm going to take the results from study 1. I'll call this first study I do, I'll call that study 1, and I'll put my results in this table here. So and I'll have one column for each correlation that I estimate. So if I only have 3 items, I'm only estimating 3 possible correlations. That makes things nice and simple. If I had a longer questionnaire, I'd have a bunch more columns to estimate. But because I only have 3 possible correlations, 3 possible pairs to look at, that makes things fairly concise. So I will take here this correlation between item 1 and item 2, and I'm just going to put that there. The correlation between item 1 and item 3 goes right there. Correlation between item 2 and 3 goes right there. So I'm just going to take the results for study 1 and plug them into my table. And I'm looking at 3 possible polychoric correlations that I'm estimating because I only have 3 items, and I'll put those 3 correlations from study 1 right there in that first row. And then we're going to imagine that we're going to replicate our study over and over and over again. So I'll replicate my study, get another sample, and estimate those same 3 polychoric correlations. I'll call that study 2. And I'll put these, the 3 correlations for that study there. And then I replicate it again and do study 3 and put my correlations there. And do study 4 and put my correlations there. And then I'll keep doing that. I'm going to assume that I replicate my studies over and over again, say an infinite number of times. So at this point, I have a data set. Hypothetically, I have a data set that the number of rows are for each study, and if I replicate my study over and over an infinite number of times, it means I have a data set with an infinite number of rows in it, and I have one column for every possible pair of items on my questionnaire. Every correlation that I'm going to estimate, I have one column for each correlation. So imagine that I had a data set like this. Let's imagine we plugged this into SPSS or something like that, that maybe it could handle an infinite number of, this is all hypothetical, of course, but imagine we could plug a data set in that had an infinite number of rows, one row for every study we did where we replicated our study over and over and over again. And we had, say, just 3 columns here. If we had a data set like this, we could take this data set and calculate the variance-covariance matrix for this data set. That is, we're going to use, instead of people being, usually we have a study where we have each case is a different person, and we look at scores for people on variables. But this is not a data set where we're looking at where cases are people, but cases are studies. So each case is not a person, but a study. And here we don't have variables, but rather results from study. We have the correlation that we got, the correlation between item 1 and item 2 that we got on study 1, the correlation between item 1 and item 3 on study 1 and 2. And so our columns are not scores on variables, but they're scores from statistical analyses that we got. What are the correlations that we got when we ran our study? So we've got, instead of variables, we have correlations that we got from our study. Instead of people, we have items, or we have studies. But we still have a data set that has rows and columns in it. And what would happen if we were to take this data set and calculate a variance-covariance matrix of the stuff that we have in this data set? And if we did that, that would be the asymptotic covariance matrix. Let's take a little closer look at exactly what that would be. It's a little hard to wrap your mind around exactly what this would be. So let's take a little closer look at what this means to say we've calculated an asymptotic covariance matrix. So the asymptotic covariance matrix, or the asymptotic variance covariance matrix, is going to be the variance covariance matrix for a set of parameter estimates. In this case, we're looking at correlations, polychoric correlations to be specific, from different studies. So that's what we saw on our previous slide, where our rows were different studies, and our variables were, in this case, correlations, polychoric correlations that we got from each study. So we have each study, and each study produced a set of correlations, and those correlations are kind of like variables, and the studies are like cases in our study, and we're looking at the correlation that we get when we look at the correlation between these different parameter estimates, between these correlations from different studies. So that means that our asymptotic covariance matrix is going to be a square matrix, and the number of rows or the number of columns that it has will be equal to the number of elements that we have in our polychoric correlation matrix. So if I'm doing a study and I have 3 polychoric correlations that I'm estimating, if I have just 3 items and I just have 3 polychoric correlations in this matrix, and so my asymptotic covariance matrix is going to be a 3 by 3 matrix. If, for example, what if I had another item here and I was actually estimating 6? If I had a 4-item questionnaire, then I'd have a total of 6 different polychoric correlations in a 4-item questionnaire. And if I had 6 polychoric correlations in my polychoric correlation matrix, then my asymptotic covariance matrix would be 6 by 6. I'd have to have another 3 rows and another 3 columns. So however many correlations there are in my polychoric correlation matrix, if I have 6 correlations, then my asymptotic covariance matrix is going to be 6 by 6. If I have just 3 correlations, it'll be 3 by 3. Usually we have a lot more than 3 or 6 because we usually have items, usually have questionnaires with lots of items on them. So again, the asymptotic covariance matrix is the variance covariance matrix for a set of parameter estimates. In this case, we're looking at polychoric correlations from different studies. Now, that's still a little bit hard to wrap our mind around. What exactly does this mean, and what are these elements telling us? So let's take another look at that. What are these elements that we get in our asymptotic covariance matrix? So in my asymptotic variance covariance matrix, which, by the way, I realize that sometimes I'm saying asymptotic variance-covariance matrix, and sometimes I'm just saying asymptotic covariance matrix, and I'm using these interchangeably. When I want to say it the full proper way, I'm saying asymptotic variance-covariance matrix, but if I want to shorten it and abbreviate what I'm saying, I'm just call it the asymptotic covariance matrix. And actually, I think it's fairly common just to refer to it as the asymptotic covariance matrix, even though technically it's a variance covariance matrix. Just to clarify that whether I say covariance or variance covariance, either way I'm talking about the same thing here. So in my asymptotic covariance matrix, or asymptotic variance covariance matrix, however, whatever term I want to use here, on the diagonal, essentially these are actually the squared standard errors for each correlation. So we were talking about sampling error, and if I had a single statistic that I was wanting to get sampling error for, that is if I replicate my study over and over again and determine how far that statistic typically deviates from the true population parameter, that would be the standard error of the statistic. And so here we have, these are actually squared standard errors in my asymptotic covariance matrix. So this is the correlation, the polychord correlation between item 1 and item 2, and this is the squared standard error for that correlation. And then here going down the diagonal, the next one down the diagonal, here's the squared standard error for the correlation between item 1 and item 3. And then we have the squared standard error for the correlation between item 2 and item 3. So essentially, we have standard errors, or squared standard errors, for each correlation in our polychord correlation matrix. And that's maybe the most important thing, and the easiest thing to understand. We also have these covariances, and they're a little tricky to wrap our minds around. At least for me, I find it tricky to wrap my mind around exactly what this is. But essentially, this is saying what is the correlation of the covariance between two correlations. That is, if you do a study and it has a high correlation between item 1 and item 2, is there also a high correlation between item 1 and item 3? And so a high covariance or high correlation here would mean that the correlation between item 1 and item 2 is associated with the correlation between item 1 and item 3. Or we could do the same thing here. We could say if you do a study and you get a high correlation between item 1 and item 2, are you also likely to get a high correlation between item 2 and item 3? And this would be the covariance between these two. So a high covariance here would mean that if you get a high correlation between these two items, you're also likely to get a high correlation between those two items. And if we standardize all this and turn it to a correlation, this would be like a correlation of correlations. If you get if you do your study over and over again, and when this correlation is high, is that correlation also likely to be high? If the correlation between this pair of items is high, is the correlation between this other pair of items also likely to be high? So these covariances are telling us information about the correlations or the associations between correlations. If a study has a high correlation for, say, R between item 1 and item 2, will it also have a high correlation for the relationship between item 2 and item 3? That's what these covariances on the off diagonal are telling us. So now we have everything we need to do a diagonally weighted least squares procedure to our confirmatory factor analysis model. So what we're going to do is we're going to first estimate item thresholds, or actually the computer will do all this for us when we use computers. So that we'll estimate item thresholds, and from that we're going to estimate polychord correlations, and we'll create that polychord correlation matrix. And note that when we do structural equation modeling, up to this point I've been talking about a process where we start off with a variance-covariance matrix, and then we use that variance-covariance matrix to get parameter estimates, and we try to estimate parameters that will produce a reconstructed variance-covariance matrix that comes as close as it possibly can to the actual observed variance-covariance matrix. And so the whole process centers around this variance-covariance matrix from our data. And when we do diagonally weighted least squares, we're not going to use that variance-covariance matrix. Instead, we're going to use this polychord correlation matrix that we calculated. We're going to use that for everything. That will be our starting point, and when we try to get parameter estimates, we're going to try to get parameter estimates that will recreate a polychord correlation matrix that will come as close as possible to the actual observed polychord correlation matrix that we have in our sample. So everything is going to be based off this polychord correlation matrix and not off of a standard variance-covariance matrix. So that's the first key thing. And then we're going to use this asymptotic covariance matrix, or specifically we're going to use the diagonal of that matrix, which has our standard errors for each polychord correlation. And we're going to use that as a weight matrix when we do our least squares fit function. Let me go back to that previous slide we looked at when I talked about fit function. I think this is here. Yeah. So we talked about, I know it talked about how when we do least squares methods for a fit function, we calculate these residuals, which is how far the elements of our S matrix deviate from the sigma, that is our, in this case it'll be our polychord correlation matrix, how far the elements of our observed polychord correlation matrix deviate from the elements in our reconstructed polychord correlation matrix, and square that and sum it up, and we get our squared residuals. But then we're going to weight these residuals by standard errors. If a residual is based on a correlation, in this case, a correlation that's we can estimate with high precision, then that residual will be given more weight. If a residual is based on a correlation that we estimate with poor precision, that will be given less weight. So we want to weight these residuals by this W matrix. And go back to what we're, whoops, wrong way. Here we go. And this W matrix, our weight matrix, is going to be based on our asymptotic covariance matrix that we just talked about a moment ago. And actually, specifically, it will use the diagonal of that asymptotic covariance matrix, which are the standard errors for all of our polychord correlations. And so we'll use the asymptotic covariance matrix as a weight matrix in the least squares fit function. And when we put that all together, we have done diagonally weighted least squares. So at this point, we've talked about how we can build a confirmatory factor analysis model, and we've talked about the steps or the process that's involved in calculating parameter estimates for a model. And then the next question is, if we run a model and get output, how do we interpret that output and draw conclusions about our model? One of the key questions we will want to address is the question of model fit. And I will save that for our next video.